this video, we're going to look at the properties of dimension. Now, if you remember from our last video, when we talked about dimension, that was the number of vectors that are in the basis, which means they are linearly independent. We're going to start with our first theorem here, which says that we have this vector space V. S is a linear independent set of vectors from V. And suppose W is a vector such that it does not belong to the span that is built by the spanning set for S. Then the set S prime is going to be we're going to define this as S prime as just the set where we take the set S, we union it with our vector W, then it must also be linearly independent because my set S was linearly independent to begin with. If W is not part of the span made by the spanning set for S, then obviously when I add another vector that is linearly independent, then this new set that I make S prime must also be linearly independent. Then that brings us to this Goldilocks. Suppose V is a vector space of dimension t. That means it has t number of vectors to build the basis. Let my S be my spanning set, or just a set of vectors, excuse me. Let S be a set of vectors from V1 to Vm. Then, if the number of vectors in S is larger than the number of vectors in the basis, then S is a linear dependent set of vectors, and we say it's too soft. If the number of vectors in S is less than the number of vectors in the basis of V, then S does not span V, and then we say it's too hard. If the number of vectors in the set S equal the number of vectors in the basis for V, the dimension, then S is linearly independent and it will span V, which is just right. Also, if M, the number of vectors in S, equals T, the number of vectors in the basis, then S spans V, and also, because it spans V, it is also linearly independent. Another just right. So then that brings us on to our next theorem that says, if we have a proper subset, suppose that U and V are subspaces of the vector space W, so W contains both U and V, and U is properly contained in V, then the dimension of U must be less than the dimension of V. So clearly, if I have a basis, that's the dimension, the number of vectors in the basis. If this has a dimension of 3, then this must have a dimension of 2. It cannot be equal because U is a proper subset, which means it's fully contained within V. Let's take a look at the next theorem. Now suppose U and V are subspaces of the vector space, and we have the potential for equality. That means if their dimensions are equal, then they must be the same set. So what that means is they have the same number of basis vectors. Then if we know that they have the same number of basis vectors, they're actually the same set. So let's look at an example here. So let's suppose that I have this set U, and this set U is the vectors 1 and 2 and 3 and 7. And then I have this set V, which is the set 1 and 0, and then 0 and then 1. Now we know that this is the basis in R2, and we also know it has a dimension of 2. That's for V. Now if we take a look at U and we put this into a matrix in reduced row echelon form, we're actually going to get this exact same basis. We're going to get this exact same vector. So we know that these are linearly independent if we throw this in a reduced row echelon form, which means that it would reduce into these vectors. That means that their dimensions are the same and also the vectors spaces, the subspaces, are exactly the same. Now, when we look at the rank of a matrix, then the rank of the matrix is the rank of the transpose. So suppose A is an m by n matrix, then the rank of R has to equal the rank of A transpose. And that kind of makes sense because if you remember what the rank of A was, how we defined the rank of A in our last video, this was the dimensions of the column space of A. And of course the dimensions, this means the number of vectors that form the basis. So that makes sense, right? That the rank of our matrix A must also be the rank of A transpose. Because if you think about this, if we look at our other theorems and proofs, we know that from our previous theorems, there's a theorem that we had in the column and row space. There's a theorem that said the column space of A is equal to the row space of A transpose. So when we're talking about the rank, which is the number of basis vectors that we have, then that makes total sense because we can find the basis by finding the column space of A, but we can also find the basis by finding the row space of A transposed. Then that leads us to our final and interesting, nice theorem here. Again, the proof is in your book for your viewing pleasure. If A is an m by n matrix and B is in a row equivalent matrix in reduced row echelon form with R non-zero rows, those are our pivots, then the dimension of the null space has to be the number of rows minus, the number of columns minus the number of pivots. The dimension of my column space must be equal to R, that is the number of pivots. Columns. The dimension of my row space has to also equal R, that is the number of pivots. And then the dimension of my left null space must be equal to the number of entries, the number of rows, minus the number of pivots. So this is a really nice theorem if we're trying to quickly determine the size or the dimension of each one of these spaces.